Out there in the vast darkness of space, hidden among the countless stars, lie objects so strange and powerful they defy everything we know about physics. These cosmic lighthouses, known as pulsars, send out beams of energy so precise they could guide alien civilizations across galaxies. But here's what will truly blow your mind. Some of these pulsars are so far away their light has been traveling longer than Earth has existed just to reach us. Today, we're diving into 25 facts about the universe's most distant pulsars that will make you question reality. You'll discover how some spin faster than your kitchen blender, how one literally devours its companion star, and how these cosmic oddities might hold the key to uncovering dark matter. By the time we're done, you'll see the night sky in a whole new way. So buckle up, we're about to journey to the edge of the known universe, where the strangest and most mysterious objects are waiting to be discovered. Now let's shine a light on what pulsars actually are. Imagine a lighthouse standing tall on a rocky coast, its beam slicing through the darkness with rhythmic precision. Pulsars are the universe's version of that lighthouse, except instead of guiding ships, their beams sweep across the cosmos, signaling their presence to anyone watching. These incredible objects are born from the violent deaths of massive stars. When a star many times heavier than our Sun runs out of fuel, it doesn't just fade away. It explodes in a cataclysmic supernova, leaving behind an ultra-dense spinning core. This core, packed with more mass than the Sun into a sphere no wider than a city, becomes a neutron star. But when that neutron star is tilted at just the right angle, its powerful magnetic fields funnel radiation into twin beams that shoot out from its poles like cosmic searchlights. Here's where the magic happens. As the neutron star spins sometimes hundreds of times per second, those beams sweep past Earth like the rotating light of a lighthouse. Every time a beam points in our direction, we detect a pulse of radiation, which is why we call them pulsars. The regularity of these pulses is so precise that some pulsars rival atomic clocks in accuracy. Take the famous Crab pulsar, born from a supernova observed in the year 1054. It spins 30 times every second, and its flashes are so predictable you could set your watch by them. But not all pulsars are created equal. Some, known as millisecond pulsars, spin dizzyingly fast, up to 700 times per second, thanks to stealing material from a companion star. Others, called magnetars, have magnetic fields so strong they'd rip the atoms in your body apart from thousands of miles away. Yet despite their differences, all pulsars share one thing: they're nature's most perfect cosmic clocks, their rhythmic beats echoing across the universe long after the stars that birthed them have vanished. Next time you look up at the night sky, remember, some of those faint, distant twinkles might actually be the flashing beacons of these incredible celestial lighthouses. Now let's take a journey to the edge of the observable universe, where the faintest whispers of pulsars still manage to reach us. Among these distant beacons, one stands out as the reigning champion of remoteness, the farthest known pulsar, whose light has been racing through the cosmos for billions of years before finally brushing against our telescopes. To put that into perspective, this pulsar's light began its journey when Earth was little more than a swirling cloud of gas and dust, long before the first single-celled organisms appeared. Detecting something so unimaginably far away is no small feat. Imagine trying to spot a single blinking firefly from thousands of miles away while standing in the middle of a bustling city. That's the level of difficulty astronomers face when hunting for these ultra-distant pulsars. Their signals are incredibly faint, often drowned out by the cosmic noise of closer stars, interstellar gas, and even human-made radio interference. To make matters more challenging, the universe itself acts like a funhouse mirror, bending and distorting light as it travels through galaxies and dark matter. This effect, known as gravitational lensing, can sometimes magnify distant objects, but it can also scramble their signals beyond recognition. So how do scientists manage to find these needles in the cosmic haystack? It starts with cutting-edge technology, radio telescopes like the Arecibo Observatory before its collapse, and now the sprawling arrays of the Square Kilometre Array act as gigantic ears tuned to the universe's faintest whispers. They sift through endless static, searching for the telltale rhythm of a pulsar's pulse. Supercomputers then analyze the data, separating false alarms like microwave ovens or passing satellites from the genuine article. But distance isn't just a hurdle, it's a time machine. When we detect a pulsar billions of light years away, we're seeing it as it was billions of years ago, a snapshot from the universe's younger, wilder days. This allows astronomers to study how pulsars behaved in the early cosmos, back when galaxies were just starting to form. Each distant pulse is a message from the past, helping us piece together the history of the universe itself. Yet for all the challenges, spotting these far-flung pulsars is worth the effort. They serve as cosmic milestones, helping us map the vastness of space and test the laws of physics across unimaginable distances. And who knows, the next record breaker might already be out there, its faint signal racing toward us, waiting to rewrite what we thought we knew about the universe's most distant lighthouses. But the story of pulsars doesn't end with their mind-bending distances. These cosmic timekeepers also serve as some of the universe's most rigorous laboratories, putting Einstein's theory of relativity through its paces. Imagine a spinning top so precise it could reveal the fabric of spacetime itself. That's essentially what certain pulsars do, thanks to their extreme gravity and clockwork regularity. Take the famous Hulse-Taylor binary system, where a pulsar orbits another neutron star. As these two dense objects dance around each other, they slowly lose energy in the form of gravitational waves, ripples in spacetime predicted by Einstein. The pulsar's arrival times, measured with astonishing precision, showed this energy loss matched Einstein's equations to within 0.2%. It was the first indirect proof of gravitational waves, earning the discoverers a Nobel Prize and cementing pulsars as relativity's ultimate test subjects. The magic lies in their precision. Some pulsars, especially millisecond pulsars, spin with a stability rivaling atomic clocks. Their pulses arrive at Earth like ticks of a cosmic metronome, predictable down to microseconds. But when a pulsar's path takes it through warped spacetime, say, near a black hole or in a tight orbit with another star, those ticks can arrive slightly early or late. These tiny deviations, detectable only by sensitive radio telescopes, let astronomers map how gravity bends time and space. Enter pulsar timing arrays, networks of these celestial clocks scattered across the galaxy. By monitoring dozens of pulsars simultaneously, scientists can detect the faint hum of gravitational waves rolling through the cosmos. These aren't the sharp chirps from colliding black holes that LIGO detects. THEYRE, Chinese letter, a low-frequency background rumble, likely from countless supermassive black hole pairs merging across the universe. The latest data hints we're on the verge of capturing this cosmic chorus, which would open a whole new window on the universe's structure. What's truly wild is how pulsars probe extremes Einstein never could have imagined. Near their surfaces, gravity is so intense that a marshmallow dropped onto one would hit with the force of a nuclear bomb. This crushes matter into states we can't replicate on Earth, letting us test whether relativity holds up where it matters most. So far, it's passing every trial, but pulsars keep pushing the limits, waiting for the day they might reveal where even Einstein's genius falls short. As we peer deeper into their rhythms, these distant lighthouses aren't just cosmic oddities. They're tools rewriting the rules of physics, one precise pulse at a time. Now let's shift gears to something that'll make your head spin literally. While pulsars are often celebrated for their precision, some take speed to outrageous extremes. Meet the millisecond pulsars, cosmic whirligigs that rotate so fast they'd leave your kitchen blender in the dust. Picture this, a city-sized object heavier than our Sun, spinning hundreds of times every single second. At their fastest, these pulsars complete one full rotation in just 1.4 milliseconds, that's 716 revolutions per second. To put that in perspective, if you could stand on the equator of one of these pulsars, you'd be moving at nearly a quarter the speed of light. How does something so massive reach such breakneck speeds? It's all about cosmic theft. Millisecond pulsars often have a companion star, and over millennia, they siphon off gas and material from their neighbor. As this stolen matter falls onto the pulsar, it transfers angular momentum like a figure skater pulling in their arms to spin faster. The result, a pulsar revved up to dizzying velocities, some of which have been spinning at these rates for billions of years without missing a beat. The reigning champion, Pulsar J1 7482446 AD, clocks in at that jaw-dropping 716 rotations per second. That's roughly 43,000 RPM, 10 times faster than a Formula One engine at full throttle. Even more mind-blowing, these speeds push the limits of physics. If a pulsar spun much faster, centrifugal forces would tear it apart, scattering neutron star guts across the cosmos. Yet somehow, these objects dance right on the edge of destruction, held together by gravity so strong it bends the rules of matter itself. What's truly wild is how we detect these hyperactive pulsars. Their beams whip around like a galactic lighthouse on overdrive, sweeping past Earth in microseconds. Radio telescopes catch these flashes as rapid-fire clicks, sometimes thousands per second. It's like trying to count individual frames in a movie playing at 100 times normal speed, a challenge that requires algorithms and supercomputers just to decode the rhythm. Yet for all their fury, millisecond pulsars are also among the universe's most precise timekeepers. Their spins are so stable that a drift of just 1 second would take 10 million years to occur. That combination of speed and accuracy makes them invaluable tools, from testing relativity to potentially navigating spacecraft in the distant future. So next time you hit the blender button, remember, somewhere out there, a pulsar is spinning faster before you've even finished mixing your smoothie and rewriting the laws of physics in the process. Now let's turn our attention to one of the most jaw-dropping feats in the cosmic playbook, pulsars that outshine entire galaxies. It sounds impossible, doesn't it? These tiny, city-sized objects, no wider than Manhattan, can blast out beams of energy so powerful they briefly eclipse the combined light of hundreds of billions of stars. But how? The secret lies in the way pulsars channel their energy. Unlike galaxies, which radiate light in all directions, pulsars focus their emissions into narrow, laser-like beams. When one of those beams sweeps across Earth, the intensity can skyrocket, making the pulsar appear brighter than the galaxy it calls home, at least in that specific wavelength. Take gamma-ray pulsars, for example. These cosmic powerhouses convert their rapid spin and monstrous magnetic fields into gamma rays, the most energetic form of light. In those wavelengths, a single pulsar's beam can outshine the entire Milky Way by a factor of 10 or more. Imagine a flashlight so bright it drowns out a stadium's worth of floodlights. That's the kind of focused brilliance we're talking about. But here's the twist: this blinding light show is fleeting. Because pulsars rotate, their beams only point toward us for a fraction of a second with each spin. The rest of the time, they're invisible to our telescopes, like a lighthouse whose beam briefly flashes in your eyes before swinging away. This on-off effect is why early astronomers sometimes mistook pulsars for flickering stars or even artificial signals. The real kicker: some pulsars achieve this galactic overshadowing while being mind-bogglingly far away. Consider Pulsar J0537+6919, a pulsar in the neighboring galaxy Messier 82. Despite being 12 million light-years distant, its gamma-ray flashes periodically outshine its host galaxy's entire output in that spectrum. That's like spotting a single light bulb in Tokyo from Los Angeles and having it appear brighter than the city itself. What fuels such extreme luminosity? It all comes down to efficiency. Pulsars waste almost no energy. Their magnetic fields, trillions of times stronger than Earth's, accelerate particles to near light speed, forcing them to emit radiation in tightly focused cones. This ruthless precision means that while a galaxy's light is diluted across vast space, a pulsar's energy is concentrated into a needle-thin spear of light. And here's where things get even wilder. Some pulsars don't just outshine their galaxies temporarily, they do it repeatedly, like a cosmic strobe light. The Crab pulsar, for instance, fires off gamma-ray pulses 30 times a second, each one briefly overpowering the Crab nebula around it. These flashes are so predictable and bright that astronomers use them to calibrate telescopes like nature's own scientific instruments. Yet for all their brilliance, pulsars aren't actually producing more total energy than galaxies. They're just squeezing every ounce of it into a beam so tight that, from our vantage point, they steal the spotlight. It's a reminder that in space, raw power isn't everything. Direction matters just as much. So next time you gaze at the night sky, remember, some of the faintest-looking dots might just be cosmic overachievers, waiting for their moment to shine brighter than anything else around them. Let's take a step back in time to one of the most amusing mix-ups in astronomy history, the moment scientists almost called the first pulsar evidence of alien life. Picture this, it's 1967, and a young graduate student named Jocelyn Bell Burnell is sifting through data from a radio telescope in Cambridge, England. Suddenly, she notices something bizarre, a series of precise, rhythmic pulses arriving every 1.337 seconds, with a regularity so perfect it defied any known natural phenomenon. At first, the team was baffled. Nothing in space behaved this way. Stars flicker, galaxies hum with chaotic energy, but this was a steady, unerring beep. Beep, beep, like a metronome ticking across the cosmos. The signal was so artificial seeming that Burnell and her advisor, Anthony Hewish, jokingly labeled it LGM1, short for Little Green Men. They couldn't rule out the possibility it was a beacon from an advanced civilization. Imagine the excitement and the nerves of thinking you might have just intercepted an extraterrestrial hello. But science thrives on skepticism. The team kept searching, and soon they found more of these signals, each with slightly different rhythms, all coming from different parts of the sky. If these were alien broadcasts, why would multiple civilizations be signaling in such similar ways? The truth was far stranger. They'd stumbled upon the first pulsar, a rapidly spinning neutron star beaming radiation like a cosmic lighthouse. The beeps were its radiation sweeping past Earth with each rotation. The discovery was monumental, but the backstory added a layer of humor to the annals of astronomy. Burnell later quipped that while they'd considered the alien hypothesis, she wasn't entirely disappointed it turned out to be just a new type of star. After all, pulsars would revolutionize our understanding of stellar evolution, gravity, and even timekeeping in space. And that original signal, it came from the pulsar now known as CPSRB 1919+21, a celestial marvel that still pulses today, no little green men required. What makes this tale so enduring isn't just the mistake, but what it reveals about scientific discovery. Even the greatest minds can be fooled by nature's ingenuity. Sometimes the universe's most ordinary objects, collapsed stars, in this case, can mimic the extraordinary so well they spark fantasies of alien contact. It's a reminder that space still holds mysteries that can make even seasoned astronomers question what they know. So the next time you hear a pulsar's steady beat, remember, to the right observer at the right moment, it might just sound like the universe saying hello. Now let's zoom in on one of the most mind-bending properties of pulsars, their unimaginably strong crusts. Imagine taking the toughest material on Earth, like steel or even diamond, and compressing it to a fraction of its size under pressures so intense that the very structure of matter changes. That's the reality inside a pulsar's crust, where gravity doesn't just bend the rules, it shatters them entirely. Here's how it works. When a massive star collapses into a neutron star, the dense core that becomes a pulsar, its outer layers crash inward with such force that protons and electrons are squeezed together, merging into neutrons. But the very surface of this stellar remnant, the crust, is where things get truly bizarre. The gravity here is 100 billion times stronger than Earth's, crushing atoms into a crystalline lattice so dense that a single sugar cube-sized chunk would weigh as much as a mountain. This isn't just dense matter, it's exotic matter. Under normal conditions, atoms are mostly empty space with electrons whizzing around a tiny nucleus. But in a pulsar's crust, that empty space vanishes. The nuclei are packed so tightly they form a rigid, uniform structure, like a cosmic eggshell, only this shell is 10 trillion times stronger than steel. To put that in perspective, if you could somehow slice a piece of this crust and drop it onto Earth, nothing in our world could scratch or dent it. Not drills, not lasers, not even the pressure at the bottom of the Mariana Trench. What's even wilder, this crust isn't static. It's under constant stress from the pulsar's insane rotation and magnetic fields, which can cause starquakes, violent shifts in the crust that release more energy than 1,000 suns. These quakes sometimes produce the mysterious glitches astronomers observe, where a pulsar suddenly spins faster, as if the universe itself hit the turbo button. And here's the kicker, we've barely scratched the surface of understanding this material. Laboratories on Earth can't replicate these conditions, so pulsars are essentially our only window into matter this extreme. Every pulse we detect carries clues about the physics of these crusts, whispering secrets about how matter behaves when the universe pushes it to the absolute limit. So next time you hear about a pulsar's steady beat, remember, that rhythm isn't just a cosmic curiosity. It's the heartbeat of an object so unimaginably dense, so unyieldingly strong, that it defies everything we know about the materials that make up our everyday world. And somewhere in that defiance, there's a whole new frontier of physics waiting to be explored. Now, let's turn our attention to one of the most dramatic relationships in the cosmos, the eerie dance between a pulsar and its doomed companion. Picture a cosmic predator, silent and relentless, slowly stripping away the life of another star. This isn't science fiction, it's the reality of what astronomers call black widow pulsars, named after the spider that famously consumes its mate. Here's how these deadly duos work. In certain binary systems, a pulsar orbits so close to another star that its intense radiation and particle winds begin to erode the star's outer layers. Over millions of years, this relentless assault vaporizes the companion, leaving behind a ghostly trail of ionized gas. The pulsar, acting like a celestial vampire, siphons material and energy from its partner, growing stronger as the other star withers away. Some Black Widow systems even accelerate this process by blasting their companions with beams of high-energy radiation, effectively cooking them alive. But the story gets even more fascinating. As the companion star loses mass, the pulsar's gravity tightens its grip, pulling the two objects closer together. This spiral of destruction can lead to some of the most extreme orbital dances in the universe, with some pairs completing a full revolution in just hours. Imagine two cosmic titans, one a spinning corpse of a dead star, the other a glowing, half-devoured giant, whirling around each other at breakneck speeds. What's truly astonishing is how these systems reveal themselves to us. Astronomers often spot black widow pulsars because of their erratic flickering. As the pulsar's beams sweep past Earth, they sometimes pass through the vaporized material of its companion, creating dips and flares in the signal, like a lighthouse shining through fog. This eerie flickering is a telltale sign of a star being slowly erased from existence. And here's the haunting twist, not all companions go quietly. Some stars fight back, their magnetic fields channeling material into violent jets or creating shockwaves that ripple through space. But in the end, gravity always wins. The pulsar's relentless pull ensures that eventually nothing remains but a faint wisp of gas and the spinning remnant of a star that once was. Black Widow systems aren't just cosmic horror stories, they're laboratories for studying extreme physics. By observing how pulsars tear apart their partners, scientists can learn about the limits of stellar evolution, the behavior of matter under intense radiation, and even the origins of mysterious fast radio bursts. Every flicker, every flare tells a story of destruction, and in that destruction, the universe whispers its deepest secrets. So the next time you gaze at the night sky, remember, hidden in the darkness are celestial predators, locked in dances of death that defy imagination. And in their lethal embrace, they teach us just how violent, how beautiful, and how utterly strange the cosmos can be. Now, let's shift gears from cosmic predators to celestial guides, because pulsars aren't just destroyers, they're also navigators. Imagine a future where spacecraft, venturing far beyond our solar system, ditch traditional GPS and instead rely on the steady pulses of dead stars to find their way. This isn't science fiction, it's a real concept NASA and other space agencies are actively exploring. Here's how it works. Pulsars are nature's most precise clocks, with spins so regular that some rival atomic clocks in accuracy. Each pulsar has a unique signature, a fingerprint of its pulse rate and beam pattern. By mapping these signatures, a spacecraft could triangulate its position in the galaxy, just like sailors once used the North Star. The idea: create a galactic GPS using pulsars as beacons. The beauty of this system lies in its range. Unlike Earth-based GPS, which weakens the farther you travel, pulsar navigation works anywhere in the galaxy. A probe heading to Alpha Centauri or even the galactic core could, in theory, check its location by listening to the ticks of distant pulsars. Engineers have already tested this. In 2017, NASA, a Neutron Star Interior Composition Explorer, or NICER, experiment on the International Space Station successfully used pulsar X-rays to determine its orbital position. But the real game changer is autonomy. Future missions to interstellar space, like a potential Voyager 3, won't have the luxury of real-time communication with Earth. Waiting hours or days for navigation updates isn't practical. Pulsar-based navigation solves this by giving probes an independent way to self-correct their course, using the universe itself as a roadmap. There's even a prototype in action. The European Space Agency's proposed mission, called Pulsar, aims to demonstrate pulsar navigation by steering a spacecraft using nothing but these cosmic lighthouses. And let's not forget the Voyager Golden Record, which included a pulsar map pointing back to Earth, essentially a cosmic "you are here" sign for any extraterrestrial finders. Of course, challenges remain. Pulsar signals weaken over vast distances, and interference from interstellar gas can muddy their rhythms. But as telescope technology improves, so does our ability to filter and amplify these signals. One day, the same dead stars that light up our skies could guide humanity's first interstellar voyages, proving that even in death, pulsars still serve the living. Now, here's something that might bend your mind. Pulsars, those ultra-dense stellar corpses, aren't just drifting alone in the cosmos. Some of them actually have planets orbiting them, and these aren't just any planets. They're survivors of cosmic chaos born from the ashes of destruction. Let's rewind to 1992, when astronomers made a jaw-dropping discovery. They found the very first confirmed exoplanets not around a sun-like star, but circling a pulsar named PSRB 1257+12. This shattered expectations, because if a planet-forming disk could exist after a supernova, the explosion that creates pulsars, then planets could thrive in places we never imagined. So how do planets form around something as violent as a pulsar? One theory is that the original star had planets before it went supernova, and a few of them somehow clung on despite the blast. Another wild idea is that the supernova's debris, what's left of the star's outer layers, collapsed into a new disk, birthing second-generation planets. Imagine that, worlds forged from the wreckage of a dead star, but don't pack your bags for a pulsar planet vacation just yet. These places are anything but hospitable. The pulsar's intense radiation bathes its planets in deadly X-rays and gamma rays, stripping away atmospheres and baking surfaces. The planets around Pulsar B 1002 plus 12, for example, are likely barren, irradiated rocks if they haven't been vaporized entirely. Yet, the strangest of them all might be the Diamond Planet, orbiting a pulsar called Pulsar J 1719-1438. This world is thought to be the crystalline core of a once massive star, crushed into something resembling a giant diamond. It's a reminder that the universe loves throwing curveballs, turning stellar corpses into treasure chests. What's truly fascinating is what these discoveries tell us. Planets aren't picky. They'll form in the most extreme environments, from the quiet disks around young stars to the chaotic aftermath of stellar explosions. And if life can adapt to Earth's harshest corners, who's to say it couldn't, in some bizarre way, exist even here? Up next, we'll see how pulsars aren't just space oddities, they're also cosmic timekeepers, slowing down in ways that reveal their secrets. Now, here's a quiet but relentless truth about these cosmic powerhouses. Pulsars don't spin forever at the same dizzying speeds. Like a top winding down on a table, they gradually slow over time, a phenomenon astronomers call spin down. But this isn't just a simple loss of momentum. It's a window into the pulsar's hidden life story. Every rotation bleeds energy. The pulsar's intense magnetic field acts like an invisible brake, converting rotational energy into electromagnetic radiation and particle winds that stream into space. The result, a slowdown so precise you could set your watch by it. Take the Crab pulsar, born in a supernova observed on Earth in the year 1054. Back then, it spun around 30 times per second. Today, it's down to about 33 rotations. A tiny change, but over centuries it adds up. This spin-down rate isn't just trivia, it's a cosmic clock. By measuring how much a pulsar has slowed, scientists can estimate its age. It's like counting the rings of a tree, but instead of bark, they're studying the rhythm of a stellar corpse. For example, the Vela pulsar, roughly 11,000 years old, slows by about 10 microseconds per year. That minuscule delay tells us not just how old it is, but how fiercely its magnetic field is tugging at it. Speaking of magnetic fields, spin-down reveals their staggering strength. A pulsar's slowdown rate is directly tied to how powerful its magnetic field is. The stronger the field, the quicker the break. Some pulsars have fields 1 trillion times stronger than Earth's, and their spin-down rates reflect that. It's how we identified magnetars, the rebels of the pulsar family, whose slowdowns are so abrupt they hint at magnetic fields capable of distorting atoms. But here's the twist, not all pulsars age gracefully. Some throw tantrums called glitches, where they suddenly speed up without warning. Imagine a figure skater pulling their arms in mid-spin, except in this case, it might be cracks in the pulsar's crust or vortices in its superfluid core causing the jump. These anomalies remind us that even the most predictable cosmic clocks occasionally surprise us. What's next? Well, pulsars aren't just slowing down, they're also cosmic messengers, and some of them are singing in a frequency we're only just beginning to hear. Now, let's turn our attention to a truly extreme member of the pulsar family, the magnetar. Imagine a cosmic object so powerful it could wipe the data off every credit card on Earth from halfway to the moon. That's the sheer force of a magnetar's magnetic field, and it's just the beginning of what makes these objects so fascinating and terrifying. Magnetars are neutron stars, just like pulsars, but they take everything to the extreme. Their magnetic fields are up to 1,000 times stronger than those of ordinary pulsars, reaching intensities that defy comprehension. To put it in perspective, if you were to get within 1,000 kilometers of a magnetar, its magnetic field would literally rip the atoms in your body apart. Even from thousands of light years away, these fields are so potent they can distort the very fabric of space around them. But how do magnetars get so powerful? The answer lies in their violent birth. Most neutron stars form from the collapse of massive stars, but magnetars are thought to arise from the most chaotic, high-energy supernova. During these explosions, the star's core doesn't just collapse, it twists and churns like a dynamo, amplifying its magnetic field to unimaginable levels. It's like taking a regular neutron star and cranking its magnetic dial to the absolute maximum. And then there are starquakes. On Earth, earthquakes happen when tectonic plates shift, but on a magnetar, the entire crust is under unimaginable stress from that insane magnetic field. When it finally gives way, the result is a starquake, a seismic event so violent it releases more energy in a fraction of a second than our Sun does in 100,000 years. These quakes can trigger colossal gamma-ray flares, some of which have been detected clear across our galaxy. In 2004, a magnetar 50,000 light-years away unleashed a blast so bright it temporarily ionized Earth's upper atmosphere, even though it was halfway across the Milky Way. Here's the wildest part: these magnetic monsters are incredibly rare. Of the roughly 3,000 known neutron stars, only around 30 are confirmed magnetars. That rarity makes every detection a major event for astronomers, offering clues about how matter behaves under conditions we could never recreate on Earth. So, while pulsars are already extreme, magnetars remind us that the universe always has something even more astonishing up its sleeve. And speaking of cosmic extremes, there's another pulsar quirk that defies expectations. Some of them don't just slow down. They suddenly, inexplicably speed up. Now, let's dive into one of the most puzzling behaviors of pulsars, the mysterious phenomenon known as a glitch. Just when astronomers think they've figured out these cosmic clocks, pulsars throw a curveball by suddenly speeding up their spin without warning. Imagine a spinning top that inexplicably starts twirling faster for no apparent reason. That's essentially what happens during a pulsar glitch, and it's left scientists scrambling for answers. So, what causes these bizarre speed boosts? While the exact mechanism isn't fully understood, there are two leading theories. The first involves the pulsar's crust, a rigid, crystalline layer just a few kilometers thick but denser than anything on Earth. Over time, as the pulsar slows down, this crust can crack under immense stress like tectonic plates on our planet. When it fractures, the pulsar's interior, which had been spinning slightly faster, suddenly transfers some of its momentum to the crust, causing the observed speed up. It's like a figure skater pulling their arms in to spin faster, except here, the skater is a city-sized star with the mass of the Sun. The second theory points to the bizarre behavior of superfluid vortices deep inside the pulsar. At these extreme densities, some of the star's interior is thought to become a superfluid, a frictionless state of matter that can flow without losing energy. These vortices, which normally align with the pulsar's rotation, can suddenly unpin and transfer angular momentum outward, giving the star a temporary spin boost. Think of it like water in a spinning bucket. If some of it sloshes outward, the bucket speeds up for a moment. Glitches aren't just rare oddities. Some pulsars, like the famous Vela pulsar, glitch regularly every few years, offering astronomers a front-row seat to study these events. The changes might seem small, a fraction of a millisecond shaved off the rotation period, but in the ultra-precise world of pulsar timing, even tiny shifts reveal volumes about the physics at play. What's truly fascinating is that glitches aren't just speed bumps in our understanding their opportunities. By studying them, scientists can probe the internal structure of neutron stars, testing theories about how matter behaves under conditions far beyond anything we can replicate in labs. Each glitch peels back another layer of mystery, showing us just how much we still have to learn about these distant cosmic enigmas. And if you thought glitches were strange, wait until you hear about pulsars that don't just speed up momentarily. They vanish entirely, only to reappear years later. But that's a story for another fact. Now, shifting our gaze from the quirks of pulsar behavior to their place in human history, let's explore one of the most poetic intersections of astronomy and artistry. When NASA Voyager probes launched in 1977, they carried a golden record, a time capsule of Earth sounds, images, and greetings. But etched into that record was something extraordinary, a map to our planet using pulsars as celestial guideposts. Imagine this: if an extraterrestrial civilization ever intercepts one of the Voyager spacecraft, they'll find a diagram showing the precise locations of 14 pulsars relative to our Sun. Each pulsar is marked by a unique binary code representing its spin rate, a fingerprint no other object in the cosmos shares. By comparing these rates to their own observations, hypothetical finders could triangulate Earth's position even across interstellar distances. It's like leaving a trail of cosmic breadcrumbs back to our doorstep. Why pulsars? Unlike stars, which drift over millennia, pulsars are staggeringly consistent. Their beams act like interstellar lighthouses, flashing with metronomic precision for millions of years. The 14 chosen for the map, including the famous Crab and Vela pulsars, were picked for their brightness and stability, ensuring they'd remain identifiable long after the Voyagers left our solar system. The map even includes the pulsars' periods encoded in binary, using the hyperfine transition of hydrogen, the most common element in the universe, as a universal unit of time. This wasn't just scientific pragmatism, it was a profound gesture. The pulsar map transforms these distant, dead stars into something deeply human, a wayfinder for strangers we may never meet. Carl Sagan, who chaired the Golden Record Committee, later reflected that it was a message in a bottle cast into the cosmic ocean. And here's the haunting beauty of it: some of the mapped pulsars could outlast not just humanity but the Sun itself. Long after Earth is gone, that golden record might still whisper our coordinates to the void. Of course, the chances of aliens finding Voyager are vanishingly small. The probes are now in interstellar space, but space is incomprehensibly vast. Yet the pulsar map endures as a testament to our longing to connect. It's a reminder that these distant spinning corpses, often studied for their physics, also anchor us to something bigger, a shared universe where even the most exotic phenomena can become part of our story. And speaking of stories, pulsars aren't just guiding hypothetical aliens, they're helping scientists hunt for one of cosmology's greatest mysteries: dark matter. But that's a revelation for our next fact. Now, let's venture into one of the most tantalizing frontiers of pulsar research: their potential role in unraveling the enigma of dark matter. This invisible substance makes up roughly 85% of the universe's mass, yet it refuses to interact with light, leaving astronomers to trace its presence only through its gravitational tug on galaxies. But here's where pulsars, those cosmic metronomes, might just hold the key to cracking the case. Picture this: as dark matter particles drift through space, they could occasionally collide with the ultra-dense neutrons inside a pulsar. Theoretical models suggest such interactions would transfer energy to the pulsar, causing subtle but measurable changes in its spin. Imagine tossing a pebble into a spinning top. The disturbance might be tiny, but it's there. By monitoring pulsars for unexplained speed ups or slow downs, scientists could potentially detect the fingerprints of dark matter. Some hypotheses go even further. Certain types of hypothetical dark matter particles, like actions, might congregate in the intense magnetic fields around pulsars. If these actions decay into detectable photons, pulsars could literally glow with dark matter's signature. It's like turning the pulsar itself into a giant dark matter detector, its beams acting as a cosmic spotlight on the invisible. One groundbreaking study focused on a pulsar named J034 plus 0534, located in our galactic backyard. Researchers scoured years of timing data for anomalies that couldn't be explained by known physics. While no smoking gun emerged, the very act of looking refines the hunt. Every ruled-out theory narrows the possibilities, inching us closer to understanding what dark matter might be. The beauty of this approach lies in pulsars' precision. Their predictability offers a clean backdrop against which even the faintest dark matter whispers could stand out. Future projects like the Square Kilometre Array aim to monitor thousands of pulsars simultaneously, creating a galaxy-wide dark matter net. If dark matter interacts with pulsars even a fraction as strongly as predicted, we might finally glimpse the universe's hidden skeleton. So while pulsars already dazzle us with their speed and brilliance, their greatest role might be as detectives in the shadowy realms of cosmology. And as we'll see next, these stellar remnants have even more surprises in store, like hosting planets made of pure diamond. Now, let's turn our attention to one of the most jaw-dropping discoveries in the cosmos, a planet that's essentially a giant diamond orbiting a pulsar. This isn't science fiction, it's real, and it's as bizarre as it sounds. Astronomers first spotted this extraordinary world in the early 1990s, circling a pulsar named Pulsar B1257+12. At first, they couldn't believe what they were seeing. Here was a planet not made of rock or gas, but of crystallized carbon, in other words, diamond. Imagine a world where the ground beneath your feet isn't soil or stone, but a vast, glittering plain of compressed carbon, harder than anything on Earth. This diamond planet, officially named Pulsar B1257+12c, but nicknamed the Diamond Planet, or even Lucy, after the Beatles song Lucy in the Sky with Diamonds, is about 5 times the size of Earth. But its composition is what truly boggles the mind. Scientists believe it's the remnant core of a once massive star that got too close to its pulsar companion. The pulsar's intense gravity stripped away the star's outer layers, leaving behind a dense, carbon-rich core. Under immense pressure, that carbon crystallized into diamond. What's even crazier is how this planet came to be. The pulsar it orbits is a millisecond pulsar, spinning hundreds of times per second. This suggests the system went through a violent past, likely a binary star system where one star exploded as a supernova, leaving behind the pulsar while the other star was cannibalized, its core transformed into this cosmic gem. The discovery turned planetary formation theories upside down. Nobody expected planets could form or survive in such extreme environments, but the Diamond Planet isn't just a cosmic curiosity. Its existence challenges our understanding of how planets evolve. Most planets form from the leftover debris of star formation, but this one was forged in destruction. It's a testament to the universe's ability to create beauty from chaos. And while it's far too hostile for life, bathed in intense radiation and subject to extreme temperatures, it's a dazzling reminder of how strange and wonderful the cosmos can be. Speaking of cosmic oddities, let's dive into another fascinating aspect of pulsars, their ability to emit light across the entire electromagnetic spectrum, revealing secrets no single wavelength could uncover alone. Now, here's something that makes pulsars even more extraordinary. They're not just one-trick ponies. These cosmic powerhouses don't limit themselves to a single type of light. Instead, they blast out radiation across the entire electromagnetic spectrum, from the lowest energy radio waves to the highest energy gamma rays, and each of these emissions tells us a different story about what's happening inside these dense, spinning remnants of dead stars. Let's start with the most familiar signal radio waves. When pulsars were first discovered in the late 1960s, it was their rhythmic radio pulses that caught astronomers' attention. These beams, created by the pulsar's powerful magnetic field funneling charged particles outward, act like a cosmic metronome ticking with unbelievable precision. But radio waves are just the tip of the iceberg. Switch to X-rays and the picture gets even more intense. Some pulsars, especially those in binary systems where they're siphoning material from a companion star, glow fiercely in X-rays. As gas spirals onto the pulsar's surface, it heats up to millions of degrees, releasing bursts of X-ray energy. This process gives us a front-row seat to the violent interactions between these stellar remnants and their surroundings. Then there are gamma rays, the most energetic form of light in the universe. Fermi Gamma Ray Space Telescope has spotted hundreds of pulsars blazing in gamma rays, some of which are invisible in radio. These gamma-ray pulsars often have beams so narrow and energetic that they slice through space like laser pointers, only detectable when they happen to point directly at Earth. The fact that pulsars can produce such extreme radiation challenges our understanding of how their magnetic fields and particle acceleration work. But perhaps the most surprising emission comes in visible light. Yes, a handful of pulsars actually flicker in wavelengths our eyes can see. Take the Crab pulsar, for example. It spins 30 times per second, and with each rotation, it flashes a pulse of visible light bright enough to spot with a backyard telescope. These optical pulses are rare, but they're a stunning reminder that pulsars aren't just radio or gamma-ray objects, they're full-spectrum cosmic beacons. What's truly remarkable is how these different emissions complement each other. Radio waves reveal the clockwork precision of a pulsar's spin. X-rays expose the violent accretion of matter, gamma rays uncover the extremes of particle acceleration, and visible light connects these distant objects to our own human-scale observations. Together, they paint a complete portrait of pulsar physics, one that no single wavelength could deliver alone. And speaking of cosmic extremes, our next stop takes us to a pulsar so mind-bendingly fast, it defies the very laws of physics as we know them. Now, let's turn our attention to a phenomenon that makes pulsars not just cosmic lighthouses, but cosmic musicians. Some pulsars don't just beam light into space, they actually sing through the fabric of spacetime itself. These gravitational wave melodies are among the most profound discoveries in modern astronomy, and they've reshaped our understanding of how the universe works. Imagine two pulsars locked in a deadly dance, orbiting each other at incredible speeds. As they spiral closer together, they don't just lose energy through light or heat, they ripple the very fabric of the cosmos. These ripples are gravitational waves, the same waves predicted by Einstein over 100 years ago. What's astonishing is that pulsars don't just produce these waves, they allow us to hear them in a way. The story begins with a pair of pulsars known as PSRB 1913+16, discovered in the 1970s. These two neutron stars orbit each other so closely that they complete a full loop in less than 8 hours. But here's the catch, their orbit isn't static. Over time, astronomers noticed the pulsars were inching closer together, losing energy at the exact rate Einstein's equations predicted. The missing energy, it was being carried away by gravitational waves, invisible tremors in spacetime itself. This discovery was so groundbreaking that it earned the Nobel Prize in Physics in 1993. For the first time, we had direct evidence that gravitational waves weren't just theoretical, they were real, and pulsars were the perfect cosmic laboratories to prove it. The precision of their pulses acted like a metronome, allowing scientists to measure tiny changes in their orbits with unbelievable accuracy. Every fraction of a second they sped up or slowed down revealed the invisible hand of gravitational waves at work. But the symphony doesn't stop there. More recent observations have shown that some pulsars might even hum on their own. Isolated pulsars with tiny deformations, imagine a spinning ball slightly squashed at the poles, could theoretically emit continuous gravitational waves, though we haven't detected them yet. If we do, it would open a whole new window into the physics of these extreme objects, letting us listen to the quietest vibrations of the universe. Gravitational waves aren't just a curiosity, they're changing how we study pulsars. By tuning into these cosmic songs, astronomers can probe the interiors of neutron stars, test the limits of general relativity, and even search for exotic physics we haven't yet imagined. And every time a pulsar's orbit shrinks by another millimeter, it's as if the universe is whispering another verse in a song we're only just beginning to understand. Next, we'll meet a pulsar so fast, it spins faster than the blades of a jet engine, pushing the limits of what we thought was physically possible. But if you thought pulsars couldn't get any more extreme, hold on to your seats because we're about to meet the universe's ultimate speed demon. Nestled roughly 18,000 light-years away in the constellation Sagittarius lies a pulsar that defies imagination. Pulsar J1748-2446 AD. This cosmic powerhouse spins an astonishing 716 times every single second. To put that into perspective, that's faster than the blades of a high-speed blender, faster than the engine of a jet aircraft, even faster than some industrial drills. At that rate, if this pulsar were the size of a basketball, its surface would be moving at nearly 1/4 the speed of light. So how does something so dense, a neutron star packing more mass than our Sun into a sphere the size of Manhattan, spin so blisteringly fast? The answer lies in a cosmic theft. This pulsar didn't start out this way. It likely had a companion star, and over millennia it siphoned gas and matter from its neighbor. As that material spiraled onto the pulsar, it transferred angular momentum, essentially giving it a gravitational push, like a merry-go-round with someone constantly throwing weights onto its edge. The result, a pulsar revved up to mind-bending speeds. What's even more fascinating is how this pulsar challenges the laws of physics. At such extreme rotation, centrifugal forces should tear it apart, yet it holds together. This forces scientists to rethink the limits of neutron star structure. Could its core be a bizarre soup of free quarks or some exotic state of matter we've never seen? Every pulse from this star is a test of our understanding, probing the boundary where conventional physics breaks down. But Pulsar J1748-2446 AD isn't just a curiosity, it's a beacon for discovery. Its rapid spin makes it a precision tool for studying gravitational waves, the behavior of matter under crushing gravity, and even the cosmic expansion of the universe. And here's the kicker: astronomers suspect there might be faster pulsars out there, spinning beyond our current detection limits. Each one we find could rewrite the rules all over again. Now, let's shift our gaze to another cosmic mystery: how pulsars act as galactic cartographers, mapping the invisible magnetic highways of the Milky Way. Now, imagine holding a compass in deep space, except instead of pointing north, it reveals the hidden skeleton of our galaxy. Pulsars do exactly that, acting as cosmic compass needles that expose the Milky Way's magnetic field. Here's how it works. As pulsars spin, they emit beams of polarized light waves that vibrate in a specific direction. When this light journeys through space, the Milky Way's magnetic field subtly twists its polarization, much like how sunlight glinting off a pond changes direction when disturbed. By studying these tiny twists across hundreds of pulsars, astronomers can trace the galaxy's magnetic field like connect the dots, unveiling its invisible architecture. The results are staggering. We've learned our galaxy's magnetic field isn't just a chaotic tangle, it has structure, with vast ribbons and loops stretching between spiral arms. Some regions resemble a spider's web, where magnetic lines crisscross to anchor clouds of gas, while others funnel cosmic rays like particle accelerators. This magnetic framework even shapes how stars form, guiding collapsing gas clouds into stellar nurseries. But pulsars don't just map the field, they reveal its surprises. Near the galactic center, the field is wildly turbulent, twisted by the supermassive black hole's gravity. In contrast, the outer reaches show eerie uniformity, as if smoothed by some cosmic hand. And sometimes pulsars catch magnetic knots, localized regions where the field abruptly strengthens, possibly marking the remnants of ancient supernova. What's next? Projects like the Square Kilometre Array will turn pulsars into ultra-precise probes, plotting the Milky Way's magnetism in unprecedented detail. This isn't just about drawing lines on a map, it's about understanding how magnetic fields sculpt galaxies, steer cosmic rays, and even influence life's chances elsewhere in the universe. Now, let's step into one of the most violent and dazzling events in the cosmos, the collision of neutron stars, and discover how these cataclysmic encounters can give birth to entirely new pulsars. Picture two ultra-dense stellar corpses, each packing more mass than our Sun into a city-sized sphere, locked in a deadly dance. As they spiral closer over millions of years, their immense gravity distorts space-time, sending ripples across the universe. Finally, they crash together in an explosion so energetic it outshines entire galaxies for a brief, spectacular moment. Astronomers call these events kilonovae, and they're cosmic gold mines literally. When neutron stars merge, the aftermath is a celestial fireworks show with lasting consequences. The collision's sheer force can fling debris into space at near light speeds, while the core may collapse into a black hole, or, under just the right conditions, reboot as a brand new pulsar. Imagine the irony: a dying star's remnant born from one explosion gets a second life through another. This newborn pulsar often spins at dizzying speeds, its magnetic field amplified by the chaos of the merger. It's like a cosmic phoenix rising from the ashes of destruction. But kilonovae don't just forge pulsars, they're also the universe's ultimate alchemists. The extreme pressures and temperatures during the merger cook up heavy elements like gold, platinum, and uranium, atom by atom. In fact, a single neutron star collision can produce thousands of Earth masses worth of these precious metals, scattering them into space like seeds. Next time you admire a gold ring, consider this. Its atoms were likely forged in a kilonova billions of years ago, ejected across the galaxy until they found their way into our solar system. These events are vanishingly rare, only a handful have been detected, but their impact is universal. They enrich galaxies with the building blocks of planets and even life, while offering astronomers a front-row seat to gravity's most extreme experiments. Thanks to observatories like LIGO and Virgo, we've now heard these mergers through gravitational waves and seen their glowing aftermath in telescopes. Each detection peels back another layer of the mystery, revealing how pulsars can emerge from the wreckage and how the universe itself is literally gilded by catastrophe. So, the next time you look up at the night sky, remember, some pulsars are born not from solitude, but from a spectacular stellar tango, one that crafts the cosmos' most exotic objects and the very elements that make up our world. Now, let's turn our attention to one of the most bizarre pulsars in the cosmos, one that plays an eerie game of cosmic hide and seek. Meet PSRB 125963, nicknamed the zombie pulsar, because of its uncanny ability to vanish and then abruptly return, as if resurrecting from the dead. This isn't some sci-fi plot, it's real, and the explanation is just as fascinating as the mystery itself. This pulsar's bizarre behavior comes down to its unusual dance partner, a massive, fast-spinning star named LS 2883. Every 3.4 years, the pulsar swoops perilously close to its companion, plunging through the star's thick disk of gas and dust. This is where things get wild. As the pulsar barrels through the debris, the surrounding material effectively smothers its radio signals, making it seem like it's vanished from our telescopes. Then, like clockwork, once it emerges on the other side, its beams reignite and the pulsar comes back to life. Imagine a cosmic lighthouse blinking out during a storm, only to shine again when the sky's clear. Except here, the storm is a swirling tempest of stellar material. But the strangeness doesn't end there. During these close encounters, the pulsar's interaction with the disk also unleashes bursts of gamma rays, some of the most energetic light in the universe. It's as if the pulsar is throwing off sparks as it battles through the chaos. Astronomers have even observed the system flaring up in X-rays, further proof of the violent turbulence at play. What makes this system truly special is that it's one of the few where we can study a pulsar interacting so intensely with another star, offering a rare window into the dynamics of these extreme relationships. So why does this matter? Beyond the sheer thrill of a cosmic zombie story, PSRB 1002-15963 teaches us about resilience. Even when shrouded in debris, the pulsar's underlying engine never stops. It simply waits for the right moment to reappear. And for scientists, tracking these disappearances and reappearances helps refine models of how pulsars interact with their environments. Every time this pulsar dies and comes back, it leaves behind clues about the physics of high-energy emissions, stellar winds, and even how binary systems evolve over time. This pulsar's eerie behavior reminds us that the universe loves a good plot twist. Just when we think we've figured something out, cosmic phenomena like PSRB 1002-15963 challenge our assumptions and keep us guessing. It's a testament to the fact that, even in the vastness of space, there's always something new and wonderfully strange waiting to be discovered. Now, let's venture into the heart of a pulsar itself, where the laws of physics as we know them start to unravel. These cosmic powerhouses don't just dazzle us with their beams, they're also laboratories for the most extreme matter in the universe. Inside a pulsar, the density is so unimaginably high that a single sugar cube-sized chunk would weigh as much as a mountain on Earth. This isn't just heavy, it's a regime where atoms cease to exist as we recognize them. Under such crushing gravity, electrons are smashed into protons, transforming them into neutrons. That's why pulsars are often called neutron stars, but even that label might be too simple. At these densities, matter could be doing something far stranger. Scientists suspect the cores of pulsars might contain exotic states like quark-gluon plasma, a primordial soup of particles that hasn't existed freely since the first microseconds after the Big Bang. It's like finding a frozen relic of the universe's birth hidden inside these spinning remnants of dead stars. What makes this so groundbreaking is that we can't recreate these conditions on Earth, no matter how powerful our particle colliders are. Pulsars are nature's own high-energy experiments, pushing matter beyond the limits of our textbooks. For instance, some theories suggest that pulsar cores might host strange matter, a bizarre form where quarks themselves break down into even stranger particles. If proven true, this could redefine the very building blocks of reality. And here's the kicker: pulsars might be hiding even weirder secrets. Some models propose that their interiors could contain superconducting fluids or crystalline lattices of neutron-rich material, structures so dense they vibrate like gongs, sending ripples through spacetime itself. These vibrations, known as starquakes, could explain sudden pulsar glitches where their spin rates abruptly change. Imagine a skater pulling their arms in mid-spin, but on a cosmic scale, with forces so intense they warp the fabric of space. Every pulse we detect from these objects is a coded message about the physics of the impossible. By studying how pulsars bend light, emit radiation, or even slow down over time, scientists are piecing together a new understanding of matter itself. These cosmic anomalies remind us that the universe still holds mysteries too extreme for our labs, but thanks to pulsars, we're getting closer to solving them one pulse at a time. This isn't just about rewriting textbooks, it's about glimpsing the universe's most forbidden realms. Pulsars don't just challenge our understanding, they dare us to rethink what matter and reality itself could truly be. Now, let's turn our gaze to one of the cosmos's most solitary wanderers, a pulsar so isolated it makes the vastness of space feel even more profound. Meet Pulsar J0108-1431, often dubbed the loneliest pulsar, a rogue traveler drifting through the emptiness between galaxies. Unlike most pulsars, which remain within the bustling neighborhoods of their home galaxies, this one has ventured into the intergalactic void, a cosmic castaway with no stellar companions for millions of light years. How did it end up so alone? The leading theory is as dramatic as it sounds. This pulsar was likely hurled into the abyss by a cataclysmic explosion. When its progenitor star went supernova, the asymmetrical blast could have given the newborn pulsar a violent kick, like a cosmic cannonball propelling it at speeds high enough to escape its galaxy's gravitational grip entirely. Some estimates suggest it's moving at over 1 million miles per hour, fast enough to cross the distance from Earth to the Moon in just 15 minutes. That's not just drifting, that's a full-blown interstellar ejection. What's astonishing is that we can even detect it at all. Pulsar J0108-1431 is roughly 400 light-years away, which sounds close by cosmic standards, but its faint pulses are whispers against the silence of intergalactic space. Its isolation means there's no interstellar gas or dust to scatter its signals, giving astronomers an unusually clean view of its emissions. This makes it a pristine laboratory for studying the raw physics of pulsars, untouched by the messy environments of galaxies. But here's the haunting question: where is it headed? Unlike stars orbiting within galaxies, this pulsar isn't bound to any structure. It's on a one-way trip through the cosmic wilderness, destined to drift forever unless it's captured by another galaxy's gravity, a fate that could take billions of years. For now, it's a lone beacon in the dark, a reminder of how violent and unpredictable the universe can be. Yet, even in its solitude, Pulsar J0108-1431 has a story to tell. Its trajectory hints at the explosive forces that shaped it, and its steady pulses offer clues about the stability of neutron stars in the most extreme isolation. It's a testament to the fact that, in the grand tapestry of the cosmos, even the loneliest objects have something profound to reveal. As we ponder this solitary wanderer, we're reminded that the universe doesn't just create pulsars in neat, predictable ways. It flings them into the unknown, challenging us to find and decipher them, no matter how far they roam. Next up, we'll explore how future telescopes like the Square Kilometre Array are set to uncover thousands more pulsars, turning these cosmic oddities from rare curiosities into a thriving field of discovery. The age of the pulsar is just beginning, but as we look ahead, the story of pulsars is far from over. It's on the brink of a seismic shift. The next generation of telescopes, with capabilities that dwarf today's instruments, are poised to unveil a hidden universe of these cosmic beacons. Leading this revolution is the Square Kilometre Array, or SCAR, a colossal observatory spanning 2 continents, Africa and Australia, with thousands of antennas working in unison. When completed, it will be the most sensitive radio telescope ever built, capable of detecting pulsars so faint and distant they're currently invisible to us. Imagine a cosmic census on an unprecedented scale. Current estimates suggest SKA could discover tens of thousands of new pulsars, effectively doubling or even tripling the number we know today. But it's not just about quantity. Many of these will be exotic specimens, pulsars orbiting black holes, ultra-dense systems with bizarre physics, or perhaps even pulsars in galaxies beyond our own. Each discovery will be a puzzle piece in understanding the life cycles of stars, the fabric of space-time, and the laws governing the universe's most extreme environments. What makes SKA so revolutionary? Its sheer sensitivity and resolution. Picture trying to hear a whisper in a thunderstorm. That's the challenge today's telescopes face with distant pulsars. SKA's vast collecting area, equivalent to a square kilometer of antennas, will turn that whisper into a clear voice. It'll pick up pulsars obscured by interstellar gas, those buried in dense star clusters, or even ones lurking in the quiet voids between galaxies. And with its ability to monitor vast swaths of sky simultaneously, SKA will catch fleeting phenomena like pulsar glitches or rare bursts in real time. But SKA isn't alone in this quest. Other upcoming observatories like the Vera C. Rubin Observatory in Chile will complement these efforts by scanning the skies in visible light, potentially spotting pulsars that emit rare optical flashes. Together, these telescopes will create a multi-wavelength map of pulsars across the cosmos, revealing how they interact with their surroundings in ways we've never seen. The implications are staggering. More pulsars mean more precise tests of Einstein's relativity, especially in strong gravity fields. They could help us detect the universe's background hum of gravitational waves or even uncover pulsars acting as dark matter detectors. And let's not forget the potential for serendipity. Every time we've expanded our observational horizons, we've stumbled upon phenomena that rewrite textbooks. Who's to say SKA won't reveal a pulsar doing something utterly inexplicable? This isn't just about adding entries to a catalog. It's about unlocking a new era of astrophysics where pulsars transition from celestial oddities to essential tools for probing the universe. From navigation beacons for future interstellar travel to laboratories for quantum gravity, their potential is limitless, and with each new discovery, we're reminded that the cosmos still holds countless secrets waiting for the right tools and the right moment to reveal them. Now, as we bring our journey through the cosmos to a close, let's take a moment to reflect on the incredible world of pulsars we've explored together. These distant cosmic lighthouses have revealed themselves to be far more than just spinning neutron stars. They're laboratories for testing the laws of physics, clocks keeping time across the galaxy, and even potential guides for future interstellar travelers. From the mind-bending speeds of millisecond pulsars to the eerie silence of rogue pulsars drifting between galaxies, each fact we've uncovered paints a picture of a universe teeming with mystery and wonder. Think about it, pulsars outshine entire galaxies in bursts of energy. Their crusts defy the strength of steel, and their gravitational waves whisper secrets about the fabric of spacetime. They've led us to diamond planets, challenged Einstein's theories, and even tricked astronomers into thinking they were signals from extraterrestrial intelligence. And with game changers like the square-kilometer array on the horizon, we're standing at the threshold of discoveries that could redefine our understanding of the cosmos. But here's the most exciting part: this is just the beginning. Every new pulsar we find is a clue waiting to be deciphered, a puzzle piece in the grand story of the universe. What else might these cosmic beacons reveal? Could they help us crack the code of dark matter? Or might we stumble upon a pulsar behaving in ways that defy all our expectations? The possibilities are as vast as space itself. If this journey through the universe's most distant pulsars has left you as awestruck as it has me, then you won't want to miss what's coming next. The cosmos is full of mysteries waiting to be uncovered, and together we can explore them all. Hit that subscribe button and tap the notification bell so you never miss an adventure into the unknown. And let me know in the comments which pulsar fact blew your mind the most. Until next time, keep looking up. The universe has so much more to show us.